Hello and welcome! In this lecture we're going to use our pathfinding and apply it to our move action so our units can move and avoid the obstacles. Okay, so here's our game so far. We've got our complete level, we've got walls, obstacles, and so on. If I take this column, I duplicate it and I put it right there next to the player. And now if I play, then if I put my mouse over on this position and I press on T, yep, there you go, it does calculate the path. However, if I click on it, yep, the unit goes through the wall. So the units are still walking direct to their target and they are not using pathfinding. So let's refactor our move action to use the pathfinding system. But before we do, let's go over here into our testing script. And we can now remove all this code. We're going to use pathfinding in the move action, so we no longer need this for testing. So let's just remove all of this. Okay. Now we can go into the move action script. So here we are. And now before we change this to make it work with pathfinding, let's refactor the code to still work exactly the same way. So exactly moving straight to the target position. However, instead of having a single vector 3 for the target position, let's refactor this to make it work with a list of vector 3. So just change the type to list of vector 3. And for the name, this is going to be the position list. Now let's solve all of these errors. First of all, over here on the wake, we no longer need to set the target position. That was required before we implement the isActive logic. Now with that, it is no longer going to move automatically by default, so we no longer need that. And since we don't have custom behavior on the wake, we can actually get rid of this. Okay. So let's solve the rest of the errors. Let's leave the update for now. Let's go down here into the take action. Again, we still want to do the exact same thing. So let's go into the position list. Let's create a new one. And in there, we're going to place the exact same element. So just one element for the target position. So just like this. However, let's also make sure that our code works with multiple positions on the position list. So how we're going to handle that is over here on the update. And the goal is basically to follow through each position on this list one by one. So that means that we need to keep track of which position we are currently following. So up here, let's store a private int for the current position index. And then we take our action, we create the position list, and we default this one back into 0. So we have this, and then over here on our update, let's grab our vector 3 for the target position, and this one is going to be going to the position list and grab the current position index. So that is our current target position. So we do this to grab the target position, then we do all the logic exactly the same as previously. So if it is too far, we move closer, but if it is not too far, if we have reached there, if so, then instead of completing the action, let's increase the index. So go into the current position index and just do ++, okay? And then after this, let's test if we've gone past the last index. So if the current position index, if this one is bigger or equal to the position list.count, then if so, then that means we have reached the end of the list, so we have no more positions to follow. And if so, then over here we do call our action complete and we do stop moving. And also for our logic to make more sense, we should really be rotating before moving. So we rotate, then we move, and then if we reach the end, then we have action complete and nothing else after that. Okay, so that's it. And with this simple refactor, everything should still be working exactly the same. So here we are, and if I click to move there, it should still go. Yep, still goes through the wall. Okay, great, that's intentional. Now that we have this working, we can easily apply pathfinding. On the pathfinding script, over here, the function that we made to calculate a path is this one right here. So it's called findPath and returns a list of grid positions. So let's go into the move action, and when we have our take action, over here, let's go into pathfinding, access the static instance, and then we call findPath. So this takes a start and end grid position. So the start is going to be the grid position for this unit. So we can access the unit, get the grid position. And the final one is the grid position. So it's the grid position for this action. So here we have a list of grid position. So this is the grid position list. However, for our logic to work, we need to be working with world positions. So afterwards, let's just fill in the position list. So instead of doing this, let's just create an empty new list. Then let's cycle through. So do a for each grid position for the grid position. Let's actually rename this since we already have something called grid position. So let's rename this to the path grid position list, and over here call it path grid position in the path grid position list. Okay, and over here just go into the position list, and we're going to go into the level grid, access the instance in order to get the world position for this path grid position list. Okay, so that's it, super simple. And just with this, all of the code should already be working. So let's see. So here we are, and if I click to move there, yep, there you go, it now avoids that one. All right, great. Now just for testing, let's increase the action point so we can try and see if the unit can get there. So on the unit script, here we've defined the action points max. Just for testing, let's put this at 9. So here we are now with 9 points, we can move really far. So let's move all the way over there. Yep, we can do it. Let's try moving to the other side of the door. Yep, it does avoid door. Let's try moving onto there. And yep, there you go, it does go. All right, great. So all of this is already working. We can move to any position on the map. However, we still have some issues here. Basically, the way that we design our code is first we get a list of all of the valid grid positions, and then the player can click to use any of them. However, we are currently not using pathfinding when validating those positions. So for example, it says this position, which is unwalkable. It says this one is a valid position when it shouldn't be. And if we click on it, yep, there you go, we have an error because we cannot reach that position. So let's fix that. On the move action script, let's go down to where we're validating. So yep, here we have the valid action grid position list. On this, we're doing all kinds of tests. So we first check if it is valid within the level grid. We check if it's not the same one as this unit is already at. We check if it's empty. And then afterwards, let's check if it is walkable. So for that, let's expose that on the pathfinding script. So over here on the pathfinding, let's go down to the bottom. And let's make a function to expose that. So a public bool is walkable grid position. And receive a grid position for the grid position. And over here, it's super simple. Just go into the grid system, get the grid object on this grid position. And then for this one, just ask if it is walkable and return this. Okay, that's it. So on the move action, let's go into the pathfinding, the instance, check if it is walkable. Let's pass in the test grid position. If it is walkable, then we want to consider it valid. But if this is not walkable, if not, then let's skip it. All right, so let's test. And yep, right away we do see it working. So that position is no longer valid, neither is this one. So if I click on it, nope, no more errors. Okay, great. Now the next issue we have is to deal with unreachable positions. So for example here, let's move this player unit slightly in front. And then let's make some more pillars here. So put one here, one in here, then one here and one here. Okay, so all of these should be blockable. So let's see that position. And yep, over there is the issue. So that position is still saying that it is walkable. And if we click on it, again, we get the same error. So let's solve that. For that, we need to ask pathfinding if there is a way to reach this test grid position. So on the pathfinding, let's make that function. Let's make it public bool, call it has path. And we're going to receive a grid position for the start grid position and a grid position for the end grid position. Then here to test if we have a path, it's super simple. We just call find path. So we call our find path function, pass in the start and the end grid positions. And then the way that we define our find path algorithm is basically down here, if no path is found, then it returns null. So over here, if we have paths, we just need to return if this does not equal null. Okay, super simple. So on the move action, let's ask the pathfinding for that. So we ask if it has a path from the unit grid position towards this test grid position. If so, then it's valid, but if not, then we continue. Let's see. And yep, there it is. The issue is now fixed. So now that position is unreachable, so it is no longer valid. Okay, great. So we have just one final issue. To test that, let's actually get rid of these. We no longer need these, so just delete all of these columns. Okay. Then let's grab this player unit and let's put it right here. So right next to this wall. Now let's test. And if we select this other unit, yep, here we do see the issue. So it says that these positions are valid because they are valid. Technically, you can reach there. There's nothing there, so you can go there. But of course, if we click on it, the path is super long. So the unit is going to go through here, around here, here, until it reaches the target position. So right now, our logic for validating is only taking into account the max distance based on the distance to the actual unit. It is not taking into account the distance of the actual path that it's going to take to get to that position. So let's fix that. Over here on the validate logic, we need to ask the pathfinding to give us the length. However, in order to do that, you might think that you can do find path, which returns a list of grid positions, and then basically that list is in length. You might think that. However, that is actually not correct. You cannot calculate the path length just based on the list of grid positions because we don't know which ones were straight moves versus diagonal moves. The only way to know that is by looking into the actual path nodes while the algorithm is running, and then looking at the f-cost, which is the actual cost for reaching that node. So in order to get the path out of here, then that means we need to return some more data from this function. So one approach would be to make a different type that holds both a list as well as an int for the path length. Or another way to return some more data from this function is to use the out keyword, just like we saw previously on the raycast. So up here, let's do an out int path length. So we're going to have an out parameter where we're going to essentially return the path length. Then for this, like I said, the path length is going to be essentially the f cost on the end node. So before we return, let's set the path length equals the end node. Let's get the f cost. That's it. And then finally down here, when we have no path, let's set the path length equals 0. Okay, so that's it. Now let's fix any errors we have. So down here we have an error. So we're doing find path. Now in this case, we don't need the length, but since we added it to the function signature, we still need to put it here. So path length. That's it, just solving that error. And then on the move action, up here, we also have another one. So we're doing find path. Again, we don't need the length, but we still need to add it. So path length. All right, so with that, we have fixed all of the errors. Now we can go into our pathfinding script, and over here, let's make a function to get the path length. So a public int get path length. Let's receive a grid position for the start grid position, another grid position for the end grid position. Then we do our find path function, pass in the start and the end, and then pass in an out int for the path length. And after this, then we return the path length. Okay, so that's it. Now we have the length of our path. Then we can go into the move action script onto our validate logic. So here it is. Let's go into the pathfinding script, the instance. Let's get the path length, pass in the start, so the unit grid position and the test grid position. Okay, so this returns the path length. However, here also remember what we did with the path length. So if we go to the top of the file where we defined our costs, remember that we multiplied these by 10 in order to be able to work with ints instead of floats. So that means that when we have the move action, we also need to multiply it by the same amount, so it does work. So let's define an int for the pathfinding distance multiplier, and we use 10. So then here we get the path length, and we just need to check if this one is bigger than the max move distance, which is our max distance on the move. So this one multiplied by the pathfinding distance multiplier. So if it is bigger, then this is too far. So we do this. If it is this. If so, then path length is too long. And we continue. Okay, so that's it. Let's test. So here we are. And if I select this unit, and yep, there you go. Those no longer show up as valid. And the reason is because it's too far. So if we go inch by inch, if we try taking multiple turns, we can indeed still get there because those positions, they are valid, they are walkable, just way too far if we are on this side of the wall. All right, great, so everything is working correctly. Now let's just verify that everything is also working correctly with the enemies. So let's grab this enemy and let's put it like on this side of this wall. So let's test and see if they go around here. However, before we do, let's once again reset the action points, otherwise the enemy is going to shoot 10 times. So on the action points on the unit, let's reset this back into 2 and let's test. So here we are, let's end the turn and see what happens. And yep, there you go, there we see the issue. The issue is that the enemy is shooting through the wall. And this isn't just an issue with the enemies, it's an issue with the shoot action itself. So if I select, I go into shoot and I shoot that enemy, yep, I am also shooting through the wall. So let's quickly fix this. Let's go here into our shoot action and let's go down to our validation logic. So here we validate, okay. We do all of the usual validations. All right, check the enemy, check if it's an enemy and so on. Then here, let's add an extra validation. And for this one, let's do a raycast from this unit's position to the target position. So we're going to go into physics and we do a raycast. Then we need the origin vector. However, do remember that the unit world position is at the bottom of the map. It's on y of 0. In a bit, we want to implement some crates and some chest-high walls, and we want the units to be able to shoot over those. So let's make sure to not use just this units.getWorldPosition. Let's offset it by a little bit, so by vector3.up, and let's offset it by the same amount, the character height that we saw on the action camera. So let's define here a float for the unit shoulder height, and put it at 1.7. And here we offset the origin position by this much, okay? Then the next parameter we need is the direction. So let's calculate a vector3 for the shoot direction. So we get the target unit, get the world position minus this unit.getWorldPosition, and we normalize. All right, we have the shoot direction, that is the second parameter. Next up is the max distance. We just want to test from the unit to the enemy. So let's use vector3.distance, calculate the distance between this unit.get the world position and the target unit.get world position. And finally, we have the layer mask. So again, let's define the same thing. So let's call it the obstacles layer mask. So we need to go up there to define them. So let's go to the top of the file, and up here, let's make a new serialized field. Private layer mask, call it the obstacles layer mask. So then let's go down to our validation. So we're doing a raycast starting from this position at shoulder height, pointing straight towards the target unit for the distance between these two and only hitting for obstacles. This raycast returns true if it hits something and false if nothing. So we just do an if. So if this raycast, if this hits something, then that means that we are blocked by an obstacle. And if so, then we continue. Okay, so that's it. We just need to assign the obstacles layer mask. So here in the editor, let's go inside the unit prefab. And over here, let's find the shoot action, and on the obstacles, select just obstacles. Okay, so let's exit, save the prefab, and let's test. And actually here, I made a slight mistake. So I'm using the unit.get world position, but remember that we refactored this function in order to work with any unit grid position. So when we call this function, we're not necessarily using the base unit as our actual position. So let's use this and convert this into world position instead of using the world position for this unit. So define a vector3 for the unit world position, and we go into the level grid, the instance, get the world position of the unit grid position that this function returns. So this one, okay. So here we use this one instead of this. So replace this one, also replace this one, also this one, and that's it. Okay, so let's test. So here we are, and if I select that unit and I go to shoot, and nope, that one is no longer shootable. All right, great. And finally, let's see if the enemy does walk around using Pathfind in order to get closer to shoot. So if we end the turn, let's see that enemy. And yep, he is moving, he does move closer, he gets within range, and he finally shoots. Alright, awesome. So here we implemented pathfinding onto our units. We can now use the map that we've designed, and all of the units are intelligent enough to find a valid path, and we also fixed the shoot action by adding a validation so it no longer shoots through walls.